Hello everyone, my name is Raul Valda and this is my video presentation for my wireless communications class. The topic of my project is Principles of OFDM and Pilot-Based Channel Estimation. There are several objectives I had before I started this project. First of all, I wanted to make a study of some of the characteristics of a wireless communications channel to see why it is harder to have good performance in this type of channel when compared to others. Then I'm going to talk about OFDM, which is one of the most widely used modulation schemes in wireless communications, as it's used in Wi-Fi, LTE, etc. I'll talk about its principles and what are the reasons for its good performance in a wireless channel. Then I'll talk about the importance of channel estimation and a couple of methods to implement it in OFDM systems. And finally, I'll explain some simulation results that show how well these ideas work for different scenarios. Let's start with the wireless channel. When thinking about wireless communications, what we usually first think is the huge advantage that users have because of the lack of physical connection between transmitter and receiver. But by using a wireless transmission, there are a lot of problems that have to be dealt with. And one of those is multipath propagation. This property makes the transmitted signal to bounce in the wireless media against reflectors, and then divide in various copies before arriving to the receiving antenna. This is why we can model the channel as a train of impulses with random amplitude. This random amplitude is then assumed to have a normal distribution, meaning that the amplitudes of such impulses are treated as Rayleigh random variables, hence the name Rayleigh fading. Now, there are two cases that concern us, and those are flat fading and frequency selective fading. I'm going to talk about them later. Here we can see an example of a Rayleigh fading channel. In this picture, we see how the characteristics of the channel change very fast in time. Now let's talk about orthogonal frequency division multiplexing, or OFDM. OFDM is a multiple carrier modulation scheme that maximizes the use of bandwidth by taking advantage of the fact that signals are orthogonal to each other when they are separated by a certain amount in frequency. In a way, we can say that it's a combination of multiplexing in frequency with the use of a known digital modulation scheme such as BPSK or QPSK. Some people may confuse FDM with OFDM as they are similar, but OFDM is more effective than FDM as signals overlap in frequency without having to worry about carrier interference. When in FDM signals, they don't have this overlap. Here we see an example of how the spectrum of an OFDM signal looks like. In the left, we can see the contribution of each carrier to the spectrum. Here it's clear to see why the different carriers are orthogonal, since when one of the carriers has full amplitude, the other carriers have nulls instead. On the right, we can see this full spectrum for a 64 carrier OFDM signal. Here we see that the bandwidth of the signal is around 64 over t, with t being the period when the frequency of the different carriers are orthogonal. Now let's see the different components of an OFDM system. This slide contains a list of all the subsystems needed to build a complete OFDM system. For now, I'm going to the next slide to show a block diagram of the whole system to see it more clearly. Okay, here's the whole system. We start in the transmitter by modulating data using any modulation of choice, such as QPSK, BPSK, etc. Then the signal is converted to parallel form to make it suitable for the next step, which is to perform an inverse fast Fourier transform, which creates the different carriers of an OFDM signal. Now, before this step, we have this pilot insertion block, which I will explain later in the presentation. After the inverse Fourier transform, we insert a guard band if necessary to prevent inter-carrier interference with other signals, and then the signal is serialized again before the transmission. Now, on the receiver side, we first transform the signal to parallel again and remove the guard bands, which are not needed anymore. We get a full signal again by performing the inverse operation, which is the FFT, and then use the pilots inserted in the transmitter to perform the estimation of the channel. Again, more on this later. Finally, the signal is converted back parallel to serial and then sent to the demodulator, which will make the decisions to estimate the original input. Now, what are the advantages of using OFDM in a wireless channel? I would say that this scheme is extremely useful in a wireless channel because the different carriers have a very narrow bandwidth when compared to the full not OFDM signal. This is preferred for a lot of reasons, but most importantly because this makes a frequency selective channel look more like a flat fading channel. In this picture we can see the effects of the frequency selective channel on a wideband signal. Since an OFDM signal has n carriers with a bandwidth to be likely many times less than a normal signal, we see that for a bandwidth f0, which we can see is much smaller than W, the channel can be approximated to be flat fading. And even if it's not, it will still be better than having the channel we saw on the previous slide. This is, in my opinion, the best advantage OFDM has over other modulation schemes, since it mitigates inter-symbol interference, which is very hard to get rid of when dealing with frequency selective channels. Now, there are many other advantages that are important enough to mention. First of all, it's not hard to implement an OFDM system, since the most difficult operations here that may not be in other systems are the FFT and the IFFT. These are very simple to compute and do not increase the complexity of the system. The other advantage that I consider important is that OFDM has a very effective use of the available spectrum, because as we saw before, this is the carrier overlap that exists to take advantage of the orthogonality of the different carriers. Of course, there are also some disadvantages, as for any procedure. One of them is the need of linear amplifiers, because OFDM has a very high peak-to-average power ratio, and linear amplifiers are known for being very inefficient. But probably the most important thing to consider when designing an OFDM system is that the carrier synchronization needs to be very precise, because if the carriers start to move a little bit in the frequency domain, they may lose orthogonality, and most likely the bit error rate of the system is going to go up very fast. These two things are very important to consider when analyzing or designing an OFDM system. Now let's talk a little about channel estimation. Channel estimation in wireless communication systems is a process in which the characteristics of a fading channel are measured in order to modify the received signal based on that information so it resembles the transmitted signal as much as possible. There are many ways to get an estimate of the channel, and one of them is to insert known symbols, also called pilots, in the input and then get the response of such symbols to estimate the channel. Now, there are two main ways of inserting these pilots into the OFDM signal. These two are called COM type or all symbols pilot arrangement and block type or all frequencies pilot arrangement. The COM type configuration consists of placing known symbol in specific equal spaced frequencies of the OFDM stream. This type of pilot insertion is done in every single OFDM sim. So if, for example, there are n number of pilots, then it means that n carriers of the OFDM signal are used specifically for estimation of the channel. The problem with this configuration is that it does not get an estimate in every single frequency used for transmission, so those missing frequencies have to be estimated using interpolation, which in most cases is not a problem since this is a very easy operation. The block type insertion is the opposite of COM type, since instead of using all the OFDM symbols in certain frequencies, it uses all the frequencies every other symbol. The advantage of using this configuration is that there is no interpolation needed in the frequency, since the pilots are located at all frequency points of the OFDM signal. The downside is that there is some channel information missing in the time between the pilots are sent, and this gets worse if the channel has very fast fading. So there is definitely a compromise between COM type and block type configurations, and since interpolation can be done fairly easy, I think COM type configuration is a better choice. To get the estimation of the channels from the received pilot symbols, we'll take a quick look at two methods: least square estimation and minimum mean square estimation. The equations to get those estimates are shown here in the screen. We see that least squares is clearly the more simple estimation method, and while minimum mean square provides better performance, it's more complex to compute, which adds complexity to the system. Least squares is definitely easier to implement, so that's something to have in mind when choosing which estimator to use. Now let's start with the simulations. For this video presentation, I was planning to show the simulation actually running in MATLAB, but it takes around 2 minutes to get each of the 3 plots. So I'll present them here, so might as well as just show the results here in the slides. Now, having said that, There are a total of 3 different scenarios that I have chosen to study in this project. The first one is for different modulation schemes. I'll test how the system performs when using BPSK and QPSK and then note any differences. The second simulation involves using different channel lengths. Let's remember that a higher number of multipath coefficients create a more complex channel. And the third simulation measures the performance of the system for a different number of pilots. All the simulations shown here use the least square estimation method and the COM-type pilot insertion for simplicity. Here is a comparison of the system using BPSK against using QPSK. The bit error rate for QPSK modulation seems to be a little bit higher. This is different than, for example, having an AWGN channel, where both modulation schemes have the same error performance. Now let's remember that QPSK has 2 times the bit rate of BPSK, so there is a compromise that can be done here. This picture shows the performance of the system when having channels with different lengths. We see that even though performance does not get worse when the complexity of the system increases, the difference doesn't seem to be that high. This shows one of the advantages I mentioned before about OFDM, which is that it's very strong against bad channel conditions. The third and last simulation shows how the number of pilots inserted in the input affect the bit error rate of the system. It's clear that when having 4 pilots, there's not enough information to estimate the channel, which results in bad performance. Now, as the number of pilots increase, there's a lower bit error rate, but so is the amount of data transmitted, since less data can be transmitted to make space for the pilots. Another compromise is found here, as the number of pilots can be chosen depending on the needs of the system designer. Now, there are some conclusions that I could draw from this project. First of all, it's important to mention how difficult it is to deal with fading channels. The nature of the wireless channel makes it a necessity to find other ways to improve performance. Other thing is that when comparing block type with COM-type pilot configurations, I was able to see from the theory that COM-type performs better in fast fading channels because the channel is updated at every symbol, while in block type there may be a loss of channel information between symbols. In other conditions, block type may have the advantage, but then interpolation can be performed in frequency to get the missing responses if needed. For the estimation method, minimum mean square proves to be the better method, but it comes at a cost of more complexity in the system. In the simulations, the least squares method does a fairly good job of estimating the channels and give reasonable error bit rates in different situations without increasing the complexity of the system. Also, from the simulations, we can say that when dealing with fading channels, there's a difference in performance between QPSK and BPSK, while QPSK does offer twice the bit rate. This is different than in white noise channels, where there's no difference in error performance between both. We also saw that increasing the length of the channel does not affect the results greatly. There are some difference for high values of signal-to-noise ratio, but they never go beyond 3 or 4 dB. This proves what I said earlier, that OFDM has good performance over channels with little multipath and channels with more complex cases of multipath. Finally, we saw that an increased number of pilots achieve a better estimation of the channel, but this was kind of obvious. What's important is that even though there was a difference in performance, the difference was low. And let's remember that that's not convenient to increase the number of pilots in a way that most of the frequency slots of the OFDM signal are used for estimation, as the amount of transmitted data decreases. Well, this is it. Thank you very much for listening, and I hope you enjoyed the presentation.